Yeah, correct. Well, the comment here in the text, the correctness follows from the proof idea. The talking about, for example, how the ordered pairs, in other words, the states of M, they transition to other states, and when the final input symbol has been read, then if either the state, of your ordered pair, the state of your machine M, if the first member of the ordered pair is in an accept state of machine M1, then M accepts, or if the final state of machine M2, in other words the second member of your ordered pair of the state of M, if that's in an accept state of machine M2, then M will accept. Okay, so the correctness, that it makes sense, that it works, that sort of follows from the thinking and the proof idea. Right? Now, if you wanted a formal proof of the correctness, usually that involves induction, an inductive type proof, and we won't do that for quite a while. Like an example of using an inductive proof to show the correctness of a proof by construction, then here's an example, but it's theorem like 1.54. It's on page 166, page 66 of your text. Speaking of putting page numbers, I spend months, even years. I don't know if you can see it. Let me try and get an obvious example. Here for example. You can see that, but in the left margin, I've got like 3 page numbers. You can see that. I spend a huge amount of time. Like, for example, let blah 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 be defined in problem 6.10, and I want to know where that is. What page is it on? Where do I find problem 6.10? And so in the left-hand margin, I put the page number where I can find it, and it's page 246. And I spent a huge amount of time, wasted time, writing page numbers, thousands and thousands of them, for the textbooks that I will be using for these deGarisMPC courses. And so, personally, I would very much like the establishment of a new habit, a new custom, by publishers when they make a reference to some proof or references some work elsewhere in the book. They should give a page number. It's not enough just to give the ID of the theorem or whatever it is, whatever the link is. There should be like C theorem 1.98. Then it should be followed by comma P for page, and then the page number where that theorem can be found. So that you can go to it easily instead of hunting out. Where is theorem whatever. So now I have a few books, very modern ones, that do it partially. It's like it's a custom, and they're all mathematicians, not physicists. So it's a custom that it is evolving, but I would like to become firmly established and universal. So that the effort, the months and years I'm doing, can be done by one person at the publishing office. And the publisher does it, and then saves thousands, tens of thousands of technical readers from doing the same thing over and over and over again. So anyway, okay. Right. So I put the page number, so you know where this is. It's on page 66 of your text. Second edition of this text. Okay. Right. Now, fortunately, most of the construction type proofs in this whole course, okay, the course are fairly simple, and you don't need a formal correctness proof, and you don't need a proof by induction to show that the construction is actually correct, right? So that's a relief. All right. So what have we done? Sort of recap a little bit. So we've shown that. Well, we've done a proof by construction, right? We've found a machine M. We've shown that that machine M recognizes the union of two languages, A1 and A2, and therefore, any two regular languages from the set or the class of regular languages. So any two, and the result was itself a regular language. The union was a regular language. Why? Well, because we found, by construction, we found a machine, a finite automaton, M, that recognized it. Okay? Therefore, A1 union A2 is itself a regular language. And that's for any two languages, A1, A2. Therefore, the class of regular languages is closed under the operation union. Okay, that's what we've shown. Okay, so we've shown closure for that operation and for that set. Okay, so we've done it for union. Now we were talking about three different regular operations: union, concatenation, and star. So now it's the turn of concatenation. Okay. So we will try to show that, similarly to above, we'll try to show that the class of regular languages is closed under concatenation, this second operation. Right? So here's the beginning of the next theorem, 1.26 in your text. Perhaps I should have put a page number. Okay, so here's the theorem statement, remember? And as usual, there's a theorem idea, a proof idea, the overview of the strategy of the proof, the main ideas, followed by the detailed proof. But partway through, you'll see next session, we get stuck. There's a major problem. It just blocks us in our tracks. We cannot proceed. And so to proceed, we have to invent a whole new tool, very powerful new tool, made a major impact in theory of computation. The notion, the idea, the concept of non-determinism. And talking about that, I need to explain what determinism is, but that's next session, right? So here's the theorem statement for theorem 1.26. The class of regular language is closed under the concatenation operation. So the only thing that's different from the previous theorem statement was the operator label. So before we had here union, but now we've got concatenation. We're dealing with the second of the regular operations that we talked about earlier sessions. Okay, so in other words, if A1 and A2 are regular languages, any two from that class, well then A1 little circle, in other words concatenation, little circle A2 is also a regular language. Okay? So in other words, this class of regular languages, I've just got short here, Reg.Languages, okay, shorthand, is closed under the operation of concatenation. Right? The proof, well, I'll give it to you verbally a little bit, that's the main idea. The proof of this theorem proceeds in a somewhat similar way to the proof idea of the previous theorem, which was what? I don't have the number anymore. Maybe 1.25. In that you're dealing with the two machines, M1 and M2. And I'll stop there because I'm cribbing on the next session. So.